Hi, my name is Brian Caffo, and this is the lecture on blocking and adjustment. So let's start talking about this problem by putting it into a context. Imagine if you're looking at improving mobility among the elderly, and you want to do this using fitness trackers. So I think for me, the most famous fitness tracker I think is Fitbit. And you want the fitness tracker to serve as motivation for greater mobility. And you're going to do a clinical trial where you randomize half of your subjects to receive a Fitbit and the control subjects get nothing. But most clinical trials, then they get something like the Fitbit at the end of the trial to reward them for being in the study, in case you're worried about that. So you're worried that age would confound the relationship, and ideally, and likely, in fact, the age groups would be distributed in roughly equal proportions among the treated and the controls. However, if you have a smaller study, something like this might happen. You might get at the younger age group one person who is a control, at the middle age group one person who is a control, at the middle age group 3 people who are a control, and the high age group, in this case 5 people who are a control, in each of those age groups having 6 people. And then in this case, age will be aliased with control status, right? For the younger ages, fewer controls. For the higher ages, more controls. And so if you were to look at the relationship between the fitness tracker and measured mobility, you'd then be worried that it's actually associated with age. So, and this would be an unlucky arrangement, and if you had enough subjects, probably things would wash out just by probability. But because you know age is such an important factor a priori, you might want to force it to be equal within your age categories. You might want to take and get 6 people who are aged 65 to 70, and then randomize among those 6 people 3 to receive the treatment and 3 to receive the control. And this is called blocking. And it's basically the principle that if you know that an important source of explanatory variation exists as a variable, why don't you control for it at the onset, at the stage of the experimental design? Let's talk about a related problem when you don't have control over the experiment, or when you've conducted the experiment and realize that there was some sort of aliasing. So for example, you might have conducted this experiment and actually there was an aliasing. What could you have done? So you're studying the elderly still, and you're comparing the use of fitness trackers with mobility, but you're just observing the collection of people who self-select into using fitness trackers versus the controls. And so you're worried about, because it's an observational study, you're worried about lots of factors that might confound the relationship between mobility and use of a fitness tracker. However, you're very concerned about age in specific, so let's just talk about that one variable. While we would note for a full observational study, you'd be concerned about lots of things. But you're worried about the age distribution. The younger subjects are going to be more likely to pick up a fitness tracker just because of level of comfort with technology and other factors like that. And so you're worried any results you see are going to be really associated with just differential age distributions. So what's the most common way to look at this, to solve this problem? And this is the idea of adjustment. And so adjustment is the idea of looking at the relationship within levels of the confounder held fixed. So we would look at, say, for example, the middle age group. We would compare the mobility with the age group held fixed. So we're still comparing like with like. Now we may not have equal numbers of subjects in that age group, but we will have fixed the age group so age isn't varying in that comparison. Okay? So there's lots of different ways to do adjustment. But perhaps the most common and straightforward and easiest one to do is so-called regression adjustment. And this is when, if we want to look at Fitbit or not as a variable in a regression analysis, what do? We add age as another variable in that regression analysis, and that performs a sort of adjustment. And I'm going to go through some examples to show you, but also go through some examples to show you that adjustment is why you can get strange things happening when you add a new variable into a regression model. So here's a pretty simple example. So here again, the gray people are people who self-selected into using a Fitbit, and the red people are the ones who are the control, or are the ones who don't use a Fitbit. And the y-axis is a measure of mobility, and the x-axis is a measure of age. In this example, you can look, the mean for the gray faces is higher than the mean mobility for the red faces. So the unadjusted effect is large. As we adjust it, we see that there's this line of mobility with age. However, and those lines are parallel. We're going to stick with just the setting where the lines are parallel in our examples. And the lines are parallel, but the difference between the parallel lines is about the same as the difference in the mean. So adjustment didn't really do much in this case other than give us peace of mind that our effect wasn't entirely due to just differential age distributions. But notice one reason why the adjustment didn't change much. First of all, the data really suggests that the lines are parallel. But secondly, there's a large overlap. At every age distribution, you see people with both control and having Fitbits. Okay, so at every age distribution, there's a lot of overlap. So there's a lot of data to directly make this comparison. Consider this example. In this example, the marginal mean, the mean for the red group disregarding age, is higher than the mean for the gray group disregarding age. However, when we fit the regression model with age in it, we fit two parallel lines, and notice that the parallel lines would suggest that the gray group is higher than the red group, okay? That the Fitbit mobility is higher than the control mobility. And what this is an example of, this is an example where the effect would actually reverse itself. It would have gone from a significant effect, but in one direction, to a significant effect in the other direction after the inclusion of age in our regression model. So this serves as an example to show why it is when someone's reporting to you to a data analysis and you say, okay, well, I'm concerned that age may be causing this problem, and they run the analysis real quick and the effect actually reverses itself, it's because of a phenomenon like this. I would also notice, look at this particular example. Another hallmark of it is there's almost no overlap. There's almost no ages where there's direct data to compare the fitness trackers with the use of a fitness tracker with mobility. Only in this sort of middle age range is there just a couple of people who are overlapping. Otherwise, it's basically the old people don't use fitness trackers and the young people all do use fitness trackers. So this data, our results, our adjusted results, will be heavily dependent on our model. Here's an example where the marginal mean, the mean without considering age, for the control group, the red faces, is higher than that of the gray group. Again, they're lower. However, when we adjust for age, notice the lines appear to be the same. There appears to be no difference. So this would be an instance where you would have a strongly significant effect if you didn't factor in age, but once you accounted for age in your regression model, it went away. Okay, everything just lied on the same line. So if you disregarded age, so this is just an example of, again, how your effect can really change after the inclusion of another variable. Oh, and notice again, in this one, there isn't a lot of direct overlap, a lot of instances of direct comparability between the groups. If there is a lot of direct comparability, the adjustment doesn't tend to change much. And in this case, here's an instance where the mean disregarding age of both groups is about the same. But when we fit the model adjusted for age, the lines, the two parallel lines we're fitting, will be quite different in terms of their intercept, or the shift between the lines would be quite high. And so this would be an instance of when it went from a non-significant effect, if we disregarded age, to a highly significant effect when we included age. The final example, I want to make this point one more time. And what I wanted to say is, in this case, once you fit the model, there would be a big effect between the two parallel lines. They look very different in this case. However, one thing I want to mention, in this case, there's no overlap, there's no ages where we observe both control and treated group, or control and self-selected Fitbit users. So this result would be all model and no data, right? The comparison we would be making would be extrapolating the line from the gray group on upward and extrapolating the line from the red group downward. So there's no data overlap to inform this decision. So this is, this is something to think about, that regression does not handle by itself, right? It does not tell you that the comparison you're making has a lot of data. So I think it's often good to ask the people that you're managing to do some basic plots. In this case, you would want to look at the correlation of age with Fitbit use, and if it's highly correlated, then that's a problem, right? In this case, you could perfectly predict their Fitbit usage by their age. If they were above this middle age round, they all used Fitbit, and if they were below that, then they didn't use Fitbit. And whenever that can happen, whenever your confounder predicts your regression variable very well that you're interested in, then that's a problem. Okay, so thanks for listening to this lecture, and I hope you learned a little bit about two common strategies: one, blocking, something that we do as part of our experimental design, and another, adjustment, something that we do after we've collected data to try and account for confounding variables that may contaminate relationships that we're interested in. Thanks again, and I'll see you in the next lecture.